Section 12.3, we're going to look at the properties of waves. We're going to talk about a pulse and periodic wave. We're going to talk about different types of waves, transverse and longitudinal. We're going to look at the relationship between wave speed, frequency, and wave length. And then we're going to talk finally about energy and amplitude and what that means. We need to begin this idea with some definitions. So first, a wave is simply the motion of a disturbance. A wave is the motion of a disturbance. That's all it is. So you might think of waves that have to follow specific patterns or things in the back of your mind. When you think of wave, you think of the ocean and a wave like that. We're talking about anything that causes some change, some disturbance of an object in its motion. Okay? Sure. Like an earthquake, there's seismic waves that come from the epicenter of an earthquake. Yeah. Those earthquake waves follow a logarithmic scale. Are you doing logarithms in math, right? Have you done logarithms in math or no? Yeah, logarithms, earthquakes are all based on log laws. The intensity of an earthquake on the Richter scale is a log scale. Now, medium, not medium, high, low, medium. What is a medium? Or if I said traveling via a medium, or through a medium. What is a medium?
Something through which energy can travel through?
Yes, very good. Okay? Something through which something can travel through. So the material through which a disturbance travels. Good explanation, Leslie. The material through which a disturbance travels. For example, we'll get to in a minute, but what is the medium through which my sound waves are carrying to your ears right now? Air. It's a combination of nitrogen, oxygen, other stuff, but it's, our atmosphere or what's contained by our atmosphere. What is the medium of outer space? Gravity is a force, right? Or a
Yeah,
field.
I was going to say
What is the actual medium?
There is none.
There is none. It's a vacuum. Space is emptiness. So there is no medium there. Or the medium would be emptiness or lack thereof. So in a minute we're going to talk about sound. So let's talk about mechanical waves. Mechanical waves are waves that require a deformable medium to travel. Waves that require a deformable medium to travel through. For example, sound. If I'm talking right now, does anybody know how you're hearing me? Anybody have any guess as to how you're actually hearing the sound waves that I'm making with my voice?
The vibration within your ears.
Yeah, it's all about vibration there. Good, Pat. So your eardrum senses these vibrations. When I speak, the molecules in front of my mouth and up to your ear, all of your ears, are being vibrated at certain frequencies to carry that sound wave. So an example of a mechanical wave is sound. It requires a deformable medium. You need air to talk. You need some sort of an atmosphere. If you're in space, you're not going to hear anything. Obviously, if you're in your space shuttle, there's air in there, there's a medium. If you're in your space suit, there's a medium. But if your space suit broke, besides the fact that you would suffocate, obviously, in space, you tried to scream in outer space, you wouldn't hear anything. There'd be no sound. Okay? So it requires a deformable medium. Now, there's two types of waves we're going to talk about. And we're going to talk about them quickly today, and again, we're going to talk about them tomorrow. But the names are pulse and periodic. Anybody want to guess what those mean? What's a pulse versus a periodic wave? You've probably heard these words before at some point.
Well, maybe a periodic wave is something that's uniform, and a pulse is just random.
Okay? Good way of putting this. I mean, uniform versus pulse is random. Give me another example. That is right. There's more to it than just that. All right, you're on the right track. Part of it was skewed a little bit off. A pulse is definitely set, like you're saying, but you can have several pulse waves after one another. That's what you were describing. But many pulse waves, one after the other, is what a periodic wave is. So a pulse wave is literally one wave. So if I took, and I'm going to use an example of the slinky in a minute, but if I took a rope and just went like this with the rope, you would see the wave travel on the rope, right? You would see it bend. That's a pulse. But if I sat there like this with the rope for a minute, and you kept seeing these waves over and over and over, that's periodic. So a pulse wave is a single wave. A periodic wave has a source that generates continuous waves. Again, a pulse is a single wave, whereas periodic waves are waves that occur as a result of a source generating continuous waves over and over and over, pulses one after the other. What might be an example of a periodic wave? Periodic wave. Where there's a source that's generating constant waves.
That'd be like kind of boat, the things that are on boats that kind of go out every, like, say 2 seconds to see if there's like fish underneath and that kind
So
of
sonar, to be simple,
yes.
but it's something more advanced than sonar now with the fish, but yeah, sonar would be good. Sonar waves, it's constantly sending out a pulse, right? This pulse is being sent out. What else?
I mean, it doesn't continue like forever, right? But maybe like an earthquake in the ocean.
Okay, so give me, what do you mean, like an earthquake in the ocean?
Yeah, earthquake in the ocean when it creates waves going out through.
Oh, so physical waves there, yeah, that's good.
Yeah.
So, an example would be, imagine an earthquake that would cause the propagation of many waves. Over time, though, yeah, it would dissipate. So it's a source that generates waves for a little while and then dies off. Good example. What would be a pulse wave? What's an example of a pulse wave?
I was gonna say like, I don't know, it's really hard, like a tsunami really is only like one, like,
It usually comes in rows, though. It usually does come in rows, but one wave like a wave on the beach could be a pulse. Sure. One specific wave is like a pulse. That's a good example. What else? Any others you can think of?
I have a question, does like a fan count as like one?
Yeah, a fan would actually be periodic because it constantly generates these waves. Yeah. Something that anything that rotates is periodic automatically.
Those like balloon guns that you drag back and it makes the air and it just sends out one. You drag them back.
What is that called?
I think it's like air guns, and you like pull a string back and then it like hits something and then it's just a bunch of air, but it makes a huge sound.
All at once,
Yeah,
not
it's all at
continuous.
once, yeah.
Good example. Again, anything that's all one, like anything that occurs at once. So take a pebble, and throw it into the water. That's a pulse wave, really. It sends out one wave, but eventually it'll disturb and it'll slowly get like dissipated over and over. But it's really just one wave. But if you took a pebble and then you kept throwing pebbles in the same location, you're generating waves from the epicenter there, right? The waves are being propagated outward every single time. All right, so let's look at types of waves now. We're going to look at two. And we're going to try and do a quick example with the slinky to demonstrate these waves. That works pretty well with transverse, a little tougher with longitudinal. So let's start with transverse. Transverse. Here's what I remember. Okay, so here's how I understand these waves. Transverse. Think about a rope. That's what you're seeing here. Some sort of a rope. And there's a source on the end that's periodic, a vibrating blade. Imagine you pull down on this blade and let go. The blade's going to do this, right? Which is going to cause the rope to continue to make waves over and over again. But what you'll notice is this. If you, actually I can show you really much more simply with this. If you were to look, and I'll invite some people to do this actually in a second, but if you look at this, if I had waves that were going like this, up and down, like so, I can see that see the minimum of this wave, the bottom fluctuates up and down. But where my hands are, is there any motion change at all, really?
No.
They're staying fixed, right? My hands are not moving, but the top and bottom are moving up and down. This is actually a transverse wave because the vibrations are perpendicular to the motion of the wave. And it's hard to see the motion. Can you, me favor, just grab that end? All right. So, if I were to go like this, the wave is traveling between Victoria and I. You all see that? Watch, I'll do it again. I send one pulse wave. The wave goes back and forth between Victoria and I. But the vibrations of the wave are actually up and down. Like, look at my hand. I have to raise my hand and go like this to get the wave, to see the wave. In this case, the wave vibrations were this way here, but what we want to get is vertical. So to get a vertical vibration, we can start to see this. Now, the wave is going back and forth between Victoria and I, but which way is the wave vibrating? It's vibrating up and down. So what you see is that if you look at a specific instance, like right here, in this spot, you'll see that as the wave gets propagated back and forth, this is actually going up and down the whole time. It's oscillating up and down as this wave goes back and forth between the two of us. So you're seeing here, this red dot is what's showing that the wave is moving, or the vibrations are up and down, but the wave is moving left to right. So we say that the wave is, or that the vibrations are perpendicular then to the wave motion, or the wave direction. Okay, that's where the perpendicular part comes in. So to remember that transverse have perpendicular nature, the letter T, right, is an example of perpendicular lines. It's an easy way to remember. Because a lot of students seem to mix these up. There's two of them on transverse. So the letter T, right, is a right angle, perpendicular. Think about perpendicular for transverse, is the letter T. Now, if we were to pause at an instant in time, as Victoria and I were sending waves back and forth, this is what you would see right here. You would see the actual shape of the slinky or of the rope. And the shape of it is a perfect wave, and this happens to be a sinusoidal wave. Later in the year, in your math class, you're going to learn about sine, cosine, tangent waves. You're going to learn about it next year in the beginning of pre-calc, or actually throughout a lot of pre-calc. But the idea here is that we have certain terminology we can use to describe waves. So let's go ahead and look at those. First, the distance or the length of a wave, or the distance from top point to top point, or from bottom point to bottom point, is called the wavelength. This symbol is called lambda. Another one of our Greek symbols. And this represents the wavelength. Since it's the length, what do you think the units are? Good. Alright, so lambda is wavelength, it's pronounced lambda, and it is the distance between two successive crests, or two successive troughs. Clearly, what are troughs and crests from the diagram? What's another word for crest? In this case, crest could also be called a highest point, or max. Very good, highest point. And the trough is not the max, but the, anybody? Minimum, or bottom, or whatever it is, okay? So, again, we've got max, or crest, means the top of the wave at any point. Trough means the bottom of the wave. What does amplitude mean, based on what it shows in the diagram? How could you define amplitude? How could you define amplitude?
Is it like the middle of, when it makes motion, when it's not, like when it's traveling, in between?
But be geometrically, I'm saying.
Oh,
be more geometric.
Right, that's in the middle, the center, some sort.
You're right that to find the amplitude, you're on the right track. You're looking at these spots where it's like at the center where you have this point. But specifically, how proud? What's the amplitude? Would you say?
The distance from the crest, so the trough.
The distance from like the midline is called to either the crest or the trough. Either one. It's the same distance. Okay, the wave is symmetric. So it's you could also say it's the height of the wave. The amplitude is the distance from the midline to the crest, also known as the height of the wave. The height of the wave. In math class, you're going to learn about amplitude being positive and negative and how the graph looks, but you don't have to worry about that right now. What I want you to know is that amplitude is the height of the wave, or the distance, right? The distance measured from the center line to either the crest or trough. And I say distance and not displacement because I'm just talking about the positive value, whatever it is. All right, do those terms make sense? Are we clear? Any questions on what these are? Some examples you might want to jot down for transverse waves. Transverse waves. The example of a pebble thrown to a pond is a perfect transverse wave. Because the wave, right, it goes like this. It travels, the pebble hits the pond right here, and the wave does this. It travels, but what's happening though is the water is vibrating up and down, which is causing the wave to ripple through the water. So the wave is rippling left to right because the water is moving up and down. So motion up and down is the vibrations of the water, yet the wave is moving left to right, so you have the perpendicular nature, thus it's a transverse wave, a pebble thrown into water. Like a ripple, use that word. We just showed a wave on a slinky or a wave on a string as another example of transverse. And then finally, EM, electromagnetic waves, believe it or not, are transverse, but they're double. They're multifaceted. There's two parts, multifaceted. There's the magnetic part, and then there's the electric part, and they travel perpendicular to each other. So that's a little bit of more elaborate wave, but an EM wave, electromagnetic wave, is transverse also. It's a combination of two transverse waves. Transverse is more of the easy type of wave to understand, so if that's misleading or confusing, please ask. Alright, so let's go to longitudinal then. So instead of perpendicular, what do you see difference here in this definition? The word is not perpendicular now, but parallel. Alright, let's talk about this now. So hopefully this works. This slinky is totally messed up now. I really need to take metal cutters out of there and just snip it and use only part of the slinky. Because see, it's like all tangled in certain areas. I gotta do it soon. Alright, for today though. So a longitudinal wave, the way actually let me do this right here. Just because it's kind of ridiculous to just keep
Keep
it
the
in.
good times rolling.
We don't ruin this with my words anymore. Alright, so whoever helps me though, just be careful because now, I want to do it before because now it's sharp. It's like sharp, sharp metal on here. Anybody want to risk helping? Come on, Jake. Alright. So, still not perfect. I might just be like, alright. You grab the end of this one, the bolt like this, and your hand will have hold it. Okay? Alright. So earlier, what Victoria and I did was go like this, right? And you saw the wave going back and forth, left to right. This is called a standing wave, by the way, where the middle's not moving. See, the middle's not really changing. It's just the sides that are fluctuating like a guitar string. Alright, so earlier we did this. We sent pulse waves like that. And that was because we wanted vertical motion and the wave to travel this way. So I went like that. So what instead we're going to do now is, I'll do first, then you can try, okay? I don't want you to see what I'm doing. So what we're going to do, back up a little bit. I want to see. Okay, good. So what we're going to do now is the motion of the wave is still left to right, but now I want to send the wave that way, its vibrations as well as moving that way. So what you do is you would go like that, and you send a pulse this way. And if you apply a force to something, you could try, let's just settle this out for a second. So what I want you to do is imagine if you're just quickly pushing that way and back. So the pulse is being sent back and forth, and what's physically happening is this. When Jake goes like this, he's sending a little bit of a force here, and it's compressing. Then it's compressing. Then it's compressing here, compressing here, compressing here. And the compression is what's traveling. Yeah, that's why you can see this one a little better. Go one more time, Jake. Go ahead. Okay, so you're seeing the compression back and forth. It's not about vibrating. Like if I did this, we can see it vibrates up and down. But that's a transverse wave. But when we send some sort of a wave along the way, you're going to see that it's moving left to right. So that's physically what's happening here. For a longitudinal wave, the vibrations are parallel to the motion. So in this example, there's going to be, as soon as you apply a force, it's going to be compressed right there. Right? Think about it. Push a spring. What does it do? It compresses it. So you compress it. But since you're not holding the spring, that compression pushes off to the next part, which compresses the next part, which pushes off to the next part. So as a result, you get areas of the spring that are stretched and areas that are compressed. So when I send a wave down, it compresses to compress this part, and then move to compress here, it's got to stretch over here actually. So you're getting areas that are compressed, and then stretched, compressed, and then stretched, but this wave is propagating back and forth. So although the shape of it is not this right here, right? This is not the shape, clearly. How does this graph describe the motion of a longitudinal wave? And use the y-axis maybe to help you, the label. How does the graph on the bottom left describe the motion of a longitudinal wave? That's my question for you to answer. Marianne?
Well, it's not really coming down, so it's not gonna have this big Y.
Okay. It's not moving up and down, so the y is different. So clearly the y is here, density, right? And not displacement. What does it mean by density? What's density?
Is it how close the springs are?
Yeah, that's exactly right, Kat. Very good. So what she noticed was the springs are compressed here. Imagine sending two pulses, right? You send two pulses of these waves. You've got a compressed area here and a compressed area here from those both pulses. Well, where they're compressed, it's high density. Where they're stretched, it's like low density. High density, low density, meaning a lot of spring for high density, very little spring right here for low density. So you have high density, low density, high density, low density. So the nature of a longitudinal wave is still, in essence, what's called sinusoidal, or following a sine curve. Okay, it's still the same general shape, but it's not describing the actual wave itself, but the compression of that wave itself. Some examples. Here's a really good example that might make sense. It might make a little more sense, rather, I guess, than this. Think about the next time you were on, you've been to like a concert or a movie, you wait on like a really long line. Are you waiting on a line? What do? They might let in like 10 people, and then it stops, and then I'm thinking of a club or something actually. But like imagine you're going out somewhere where it's a line where they let in people only a little bit at a time. So what would happen in that? You would move up on the line, you'd stop. You move up, you'd stop. So in the line, wouldn't there be areas where people are spread apart for a little, then they compress, then they spread apart? As you move along the line, you're moving in a longitudinal nature. Another example that's synonymous to that is traffic, or analogous. I knew it was analogous. Is traffic flow. Have you ever been in traffic on like I-95 and the New Jersey Turnpike traveling somewhere? You get parts where it just stopped. Then you coast for like a minute, 60, and then suddenly you stop again. And then you coast. Whenever it's like that kind of traffic is so frustrating, that's a perfect example of this. Right? Traffic opens up, traffic, and the traffic opens up. Okay, so the idea of a longitudinal wave is very occurring in nature. It's not always what we think it is. All right, next. Sound waves are also examples of longitudinal. Sound waves, ready? I talk. The vibration of the molecules is this way. And the wave is also traveling this way. Okay, it's parallel to the wave. And the last example are pressure waves. Pressure waves. So think about storms like low pressure centers and stuff. When there's a differential in pressure, it creates an imbalance, so there's going to be waves as a result of that. Alright. This is going to be a piece of actually good, I think. So hopefully it'll work. So let's go to the next slide. Take a quick look. Alright, yeah, this is our only math part, but the math part for this section is really, really quite simple. So we're starting with the definition of velocity. Velocity is equal to displacement over time. Displacement over time. Now, in the terms of waves, the displacement is measured in what? What units?
Meters.
Which is the same units of wavelength, right? So when we're looking at waves, the displacement, the amount of distance, or not distance, the amount of position change of the wave is called its wavelength. So we start this formula by replacing this right here, replace this x with our wavelength lambda. The time it takes for a wave to occur is called the what? What is this symbol for? But what does it mean? Period. Okay, I didn't hear you. Period, good. So then we have the wavelength and we have the period of the wave, tau. Now, by definition, if you recall from class, period is defined as 1 over frequency. Right, 1 over omega. This was from section 12.1 and 12.2. So we replace tau with 1 over omega. So we get wavelength over 1 over omega. When you divide by a fraction, what are you really doing? By the? So lambda divided by 1 over omega is really lambda times omega over 1. So as a result, you get lambda times omega, giving you this formula up here. So I'll box it in. You have to know what's boxed in. It's given on your formula sheet, but that's what you're going to use. Again, I'm just showing you where it comes from. This all gets derived from our basic kinematic formulas, but it refers to waves. But what you need to know is what's in the box. So all this other stuff I'm just showing you. It's not going to be asked on that test, okay? So the velocity of a wave is equal to its frequency times its wavelength. Again, the velocity of a wave is frequency measured in hertz times wavelength measured in meters. And I can prove to you that the units are correct. Let's do that. Again, here's our formula, just to write it down. Let's look at our units. Units of frequency are hertz. Oops. Are hertz. Units of wavelength are meters. Units of velocity. Well, that doesn't seem to work, does it? Doesn't look like those balance. But what is hertz defined as? Anybody remember? From 12.1 and 12.2?
1 over second.
It's 1 over seconds. So replace this with 1 over s. M times 1 over s is n over s. Again, replace hertz, whether you do it visually or literally. Okay, replace this with 1 over seconds. A meter times 1 is a meter over seconds. So it is true. Okay, but again, hertz is 1 over seconds for that. But this is the formula you need to know. I think 2 examples? Yeah. 2 examples of this. Okay, let's look at 2 examples of this. So first, the wavelength of a sound wave produced by a middle C. That's your, on a trumpet, that's your how many people play an instrument? I know, no, he's a piano pro. Anybody else play an instrument like a trumpet or like a instrument? What do you play?
I used to play the trumpet.
Trumpet, okay. The middle C is called your B flat major for the trumpet, is that right? Or B flat chord, whatever you would use. And it produces a wavelength of 0.72 meters. Think about that for a second. We don't see sound waves. What if we did? A sound wave from a trumpet at a middle C would be 0.72 meters. This would be how long the wave actually is. Isn't that crazy to think about that? That when somebody plays that instrument, that's the length of the wave that's being sent to your ears, and your ear is able to interpret a wave almost 3/4 of a meter long. The speed of sound in air, not sounds. The speed of sound, or actually it could be sounds, any sounds, but the speed of sound in air is 343 meters per second. Now, remember, sound requires a medium that's deformable. So air can be deformed, which is why the speed here can fluctuate. So if you have sound waves going through water, as Ed said before, it's called sonar. The speed of the sound waves, the velocity changes when you're in water. Okay, the speed actually changes, so based on the medium that you're traveling through. So we have the wavelength, the speed, find the pitch of the note. The pitch, or the frequency. So this is a plug and chug. This is really easy, right? We've got this here. Given, what are we given? What variables in the equation?
Lambda, which is 0.72, and velocity, which is 3.3.
Okay, and we're trying to find omega. So solve for omega. Plug it in, plug it in. So 343 over 0.72. So it's going to be something bigger than 343, clearly, because we're dividing by a decimal or a fraction. What do we get? What do we get for this? Remember, my units are hertz for my frequency, so I could already fill those in. What's the number? What do you got, Seth?
476.38.
All right, so I'm going to say 0.4 for now. 476 hertz. 476 hertz is the frequency of a sound wave. Now, this is not to be confused with radio waves. You hear sound from a transmitter in your car that takes radio stations, takes radio waves, converts them into sound waves. The radio waves you hear are on order of like 100 megahertz. That's 100 times 10 to the 6. This is not the sound waves that you're getting in your car. You follow what I'm saying? Radio waves get interpreted by the antenna in your car, which then go through a transmitter, and then the speakers give off a sound wave, which has some frequency. Sound waves are low frequency waves. Low frequency. Now, if they're low frequency, it means that they're high wavelength. So longer wavelength is lower frequency. I know that because of this right here. Take a look. Take a look up here. If I think about this, if the velocity is the same, say it's sound for now, okay, velocity remains unchanged. If I increase the wavelength, I'm decreasing the frequency. Or if I increase the frequency, I'm decreasing the wavelength. These two things that I'm pointing to right now are inversely related to one another. Assuming this is constant, obviously. Mathematical. Calculate the wavelength. So now we're trying to find lambda. Calculate the wavelength of an X-ray, which is an EM wave, if its frequency is given as this, and all EM waves in a vacuum travel at the speed of light, which is this. So what do I know? What variables do I know? These problems are all about identifying. They're not really difficult as far as math is concerned. Just identifications. What do I know? And use units to help you if you don't know. 3 times 10 to the 8 is given in meters per second. So what variable is that? Velocity. Good, Steph. And that's the velocity of light in a vacuum. Some people, well, we're going to call that later in the year C. Little c is the speed of light. It's a constant. We'll call it V for now. Then what about hertz? Hertz are units of what? Frequency. So that's going to be this part. Now it's 3 times 10 to the 12 megahertz. What does mega mean? Because it's not just hertz, it's megahertz.
1,000. No, we don't.
You're on the right track. It's in that direction, but it's the next highest level up, or next 3 tier up. Because 1,000 is kilo, remember? And mega is 1,000 kilos. And so you think about that. Mega is 1,000 of kilos. 100,000, or times 10 to the, a million. A million, I apologize. Yeah, because you're adding 3 zeros to 1,000, making it a million. So it's really just times 10 to the 6 after that. Again, this, I'm underlining in red, that's what mega really means. Times 10 to the 6, which is a million. And a million. It's 1,000,000. That's what a million is, by the way, right? Like Kat said, 100,000, and another zero. It really becomes 1,000,000, but we just call that a million. Okay? 1,000,000. That's what a mega is. So as a result, 3 times 10 to the 12 times 10 to the 6 is times 10 to the, thank you, 18. Know your laws of exponents. Let's go. Should be quick. The stuff you've done in math. So you've got formula V equals omega lambda. The goal is to find lambda. So divide by omega. All right, V over omega, that gives you lambda, which is equal to 3 times 10 to the 8 over 3 times 10 to the 18. Now, do you really need your calculator for this? 3 over 3 is? Thank you. 10 to the 8 over 10 to the 18 is 10 to the? Negative? Good. And this is in meters. So look at the difference here. A sound wave, its wavelength was 0.72 meters. But an EM wave of, was it X-ray, right? X-ray? An X-ray is less than a nanometer. Why do you think now X-rays are able to show up what's in your body? These waves are so small, so they can penetrate through your skin. That's how X-rays work, really. If I were to yell loud enough right in front of maybe like in front of your body, the sound waves will bounce off, but they're not going through you. X-rays actually do go through you. And what you're getting when you get your X-ray, the waves go through you and show up on that screen. You know, they put that screen in the back, and then they take like a snapshot or a photo of it. It's what's going on inside of you. It's how the speed changes. It's able to sense the density and what's actually happening from an X-ray. So bones, when an X-ray travels through bones, travels a different way when it travels through skin or through blood. So that's where you get that outline of the bones when you do an X-ray. Okay, it has to do with the speed of the wave as it travels through your body, because it changes. So X-rays really are a function of the speed itself. Now, we know that the speed of anything in a vacuum is this number. But once it hits your body, is it any longer in a vacuum? No. It's going through your body. So the velocity is going to change. That change in velocity is what the readout is with your X-ray scan at the end. Okay, that's how X-rays really work, because the wavelength is so minute. Okay, smaller than a nano and 10 to the negative 9. Smaller than even that. All right, great job so far, guys. Last thing, I want to point out some things. No examples, we're doing math. So I want to talk about waves and energy and the relationship between the two. So first, the rate at which a wave carries energy is called its amplitude. Or, sorry, it depends on the amplitude. Again, the rate of energy transferred, give me like 3 more, not even, 30 seconds. The rate of energy transferred by a wave depends on amplitude. Second, actually, I'm going to pause.